Hey, hello. What's next in differential equations is chapter 5.1, spring mass system. So I'll put all this on the board and I'd like to try to explain it to you. Let's start over here. What we talk about, well, actually, see this thing in the box? That's our DE. Notice this is a second order DE with constant coefficients, M, beta, and K. And maybe it's maybe it's non-homogeneous, where we have a function over here, or maybe it is homogeneous when that equals 0. But in general, this is our second order DE with constant coefficients that we learned about in chapter 4. But we derive this by hanging a mass from a ceiling on a spring. The spring has a natural length L. When you hang the mass on that spring, it stretches at a distance S. And that puts you at x equals 0. That's just hanging there in equilibrium. You know, what we do is we call above equilibrium negative. We call below equilibrium positive. So that's the way we set this up. X is the position of the mass at any time, and x of t is the position of the mass at any time. That's the solution to the differential equation when we solve it. X prime of t is the velocity, of course, if that's position. X prime is the velocity, and x double prime is the acceleration. So what we do is we pull this down a little distance and we let it go, or maybe we give it a little push. Those are the initial conditions for the differential equation. We'll talk about those later. But once we set it into motion, it oscillates, of course. And what are the forces that are acting on this mass? So weight is one of the forces acting on it, and it's in the downward direction, which is positive. So there's the weight, positive mg. G is gravity. The restoring force of the spring is Hooke's law, the spring constant K multiplied by how far it's been stretched from the natural length. So when we pulled it down, it was stretched S plus X. The damping force is like air resistance, or, you know, this spring could be in air, could be in water, mass could be moving in various substances where we have some friction, or a damping force, which is proportional to the velocity. So it's beta x prime, where beta is some constant of proportionality. And it's opposite the direction of motion. This is opposite, these are negative. And then there could be an external force, like maybe every time the mass comes down, I give it a little push. That would be an external force. Or maybe there's a little motor attached to the mass. It's pushing it and pulling it up and down. And according to Newton's second law, the sum of all the forces is ma, mass times acceleration. So we use that to derive this DE. Here we are. The sum of all the forces is ma, so I wrote that here. Ma, that's my a, because x double prime is acceleration. Ma is the sum of all the forces. So there's my weight, there's my restoring force of the spring, my damping force, and my external force. When you distribute that k, you get this mg minus ks minus kx minus beta x prime, and this goes to 0, and the reason this goes to 0, that mg minus ks, is because if we pause before we put this in motion and analyze it at equilibrium, it's just hanging there at equilibrium, and there's only two forces acting on it, the weight, mg, and the restoring force of the spring, but it's only been stretched s, so the restoring force is ks, and those two forces add up to, you could say it adds up to ma, but it's not in motion, so a is 0. So the sum of those forces in equilibrium adds up to 0. So mg minus ks is 0. That's a true fact. I use that here to call that 0. That leaves me with mx double prime equals negative kx, negative beta x prime plus f of t. Move these two terms over, and you have what we've been shooting for. This is our second order DE. We will pull this mass down. There will be an initial distance, an initial condition where we We set it into motion sometimes, some initial x naught, and we might give it a little push when we let it go. So there's some initial velocity. I'll call that v naught. So we'll have a second order dE with initial conditions, and we can solve it in this context. You know, when do you hang a mast from a ceiling? When do you really do that? Probably not, but it describes oscillating behavior. There's an analogy for circuits. There's an analogy for LRC circuits. I could try to explain that to you, but I think that's enough for this video. So this is the DE we'll be working on. I'll do an example in a minute. Thanks.